we're not going to cover example 4.5. Okay, let's look at the last subtopic, analysis model, when now object move in a uniform circular motion. Okay, number one, kita kena define dulu. Uniform ni apa? Uniform represent the idea that it move at constant speed. Constant speed. So, every time it move at the same value of v, we call it as uniform. And the whole idea of this model is particle in uniform circular motion. Right? Now, okay, bear in mind, even though it moves at constant speed in a circular path, it still have an acceleration. The reason, another way of looking at it is that it's changing in terms of the direction. So, since velocity is a vector, and though the magnitude is the same, but it does undergoes what we call as change in the direction. Okay, change in the direction. For instance, as you can see there, okay, partial of the figure shows that at one time it's located here, tangentially moving in this direction, tangentially moving in this direction. So it does keep changing the direction. A bit lost, madam. Alright. Now try to imagine a car making a turn. Making a turn. Kona lah. So kalau dia terbabas, slip, where would it go? Due to the concept of inertia, it will go at the same direction as the current speed. In that sense, dia akan terbabas tangent to the circumference. Understand? So, in short, their velocity is always tangent to the circumference. Okay? Velocity is always tangent. Now, the changes of this velocity in form of vector like this. You can see here the initial presented by this arrow and the final can be presented by this arrow. And hence you see that we can rearrange the V. Okay. However, we can see is that there is a change of the velocity. There is change in terms of the velocity. Right. So, to wrap up the whole idea, even though any object or you running in a circle at the same speed, but your velocity are different. Even though you are running at the same value of v, but your velocity differ because you keep changing your direction. So, you are supposed to go straight in front, but corner sikit, making an angle. And then again making an angle so that now you are now in a circular path. Right. So, conclusion, yes. And in the case just now, right, that acceleration vector would be pointed towards the center of the circle. Towards the center of the circle. Okay, as such shown here. So, you will find that the change in the velocity or what we call as acceleration is towards the center. Now, there is another acceleration just now mentioned here. Acceleration vector, because there is a change in the velocity and therefore resultant the direction is towards the center. So, what is this acceleration? What is this acceleration? It is something you have seen earlier in high school. We call it as centripetal force and centripetal acceleration. Force is because of the product ma. Acceleration is the acceleration itself. Right? So, what is this acceleration? I'll give you a hint. It's supposed to be divided with r. So, what are these? Okay, let's have a look. Now, since it's a uniform motion, like mentioned earlier, our V remain the same, right? Our V remain the same. The drawing, okay, and you will find that when we draw the vector, okay, perpendicular to the position vector, okay, both triangle and their ratio are the same. Okay, the R, okay, delta R is the same as our delta V. Their ratio. If one is 3, the other turns out to be 3. But in terms of the magnitude might be different. Contohlah, 5 divided by 5 is 3. 30 divided by 10 is also 3. So that's the idea, that their ratio is the same. However, their value might be different. Now, this correlation would now be used to get the centripetal acceleration. How? By considering acceleration is V, delta V over time interval. So that's okay. And then, so the expression earlier, we are going to divide with time. So both are to be divided with delta time, and the V would be transferred over here because we would like to see the concept of acceleration is the product of delta V over delta T, and at the same time V times delta R over delta T. Right, I'm going to highlight something. Delta R over delta T, when T is approaching 0, the terms in stateless, you will find that this would turns out to be V. Okay, approaching the speed of V, the instantaneous speed at that location. So from here, what do you see? As you simplify, you have V squared over R. So our missing piece to get AC just now is speed. Okay, speed squared over the radius of the circle. So this is it, centripetal acceleration. Now, we have another things that to note as well. We call it time or period. Period is time taken to complete one cycle. Time taken to complete one circle. Understood? So, if you are traveling in one circle, the period is starting at this location and ended at this location. So how it can be calculated? Okay, we can use the version of this one. That speed is distance travel divided with time. However, since we are putting period, time taken to complete one cycle, and this x is one circumference. That's one circumference. So arranging it once again, arriving with this expression. If you find that you have a hard time to remember this expression, just go with this expression. That distance, the circumference, one circumference divided by a period, and then rearrange it. Now we have another, what we call as angular speed. So we have speed, we have angular speed. So speed would be a measurement of the distance traveled divided by the time to complete that travel distance. So because we are looking at term symbol T, so T is defined as time to complete one cycle, then distance is one cycle, the circumference of one cycle. Now angular speed represent distance traveled but in a form of angle, So this speed, but distance now is not distance but it's actually angle. So within one cycle, this is one cycle, the angle measured would be 2 pi rad. 2 pi rad. Remember, rad is the unit, so we don't have to put it down here. And time taken would be t. So we have another expression here. Now, this omega, when we do combination, 2 pi t, and then combining with this idea into this expression, at the end of the day, you find that you arrive with the linear expression, R omega, where relationship between V and omega. So we find that is a relationship between angular and translational, meaning that if let's say you have a V in unit meter per second, but you would like to convert into unit angular quantities. So this is the correlation. Okay, this is the correlation. Alright. And therefore, okay, so AC just now, remember that it's V squared over R, and this V is R omega. So that's how you arrive with R omega squared over R, or simplify R omega squared. Okay, R omega squared. Right. Let's now look at the what we did just now, the general idea. So AC is V squared over R. Period is time taken to complete one cycle, where you can use this version that V is travelling distance within one cycle, 2 pi r, circumference, and divided by T. And then we arrange into this expression 4.22. While angular speed, therefore, is actually almost like omega, and V are similar to one another, except that the angle is measured in form of rad divided by T, and this is 2 pi, right? And then when you combine between them, you have them V is equivalent to R omega. Okay, let us now look at example 4.6, the centripetal acceleration of the Earth. Okay, so what will be acceleration, centripetal acceleration of the Earth if it moves in its orbit around the Sun? So the general expression is V squared over R. So the R that we are talking about is the R. This is the Sun, and this is the Earth. So Sun emanating the heat, and the Earth. So we are talking about from here to here. This is the R that we should consider. However, we are not that sure of the value of V. So we are going to opt for the expression travelling distance of the circumference 2 pi r and divided by the time taken to complete one cycle. To complete one cycle is 1 year time. So 1 year time is convert into second this much. Right. Nevertheless, you will find that as you simplify this expression, 2 become 4 pi squared r squared over t, and then r can be cancelled out. So having simplified version of 4 pi squared over times r over t squared. Now, just substitute. However, you might ask me, where do I get R? As R is usually will be given in the exam. Don't memorize it. In this case, they have given you the value 1.496 to the power of times 10 to the power of 11 meters. So, simplified. Notice that the unit, this is acceleration. So, the unit is still meter per second squared. Now let's look at the angular speed. What does angular speed present? Angular speed is similar to speed, except that if you remember, we have two expressions, V R omega, but this is the one that we would like to have. Okay, you can choose this expression V and then divide by the R. Yes, you will arrive with the answer. Okay. So 2 pi R over T and then divide by the R. So you will arrive with the answer. However, looking at the answer provided here, okay, omega is distance travel in form of angle divided by one cycle of time. So one cycle of time is 1 year. In the time of second, this is how much is it? So this angle is 2 pi rad. One cycle has an angle of 2 pi rad. Now, since rad does not we will not say rad is dimensionless. So units left is only second. That's the reason why the answer is over second. Now let us have a look at 4.5, subtopic 4.5, tangential and radial acceleration. Now in this situation, we are going to see that we are not going to have a V constant. So V is not constant. V is not constant. So in this subtopic, you are going to see not only we have what we call a value of acceleration towards the center, where the name now is called A radial, we are as well going to have an acceleration occurring tangent to the circumference. Tangent to the circumference. Alright, now, so you will find as overall when we talk about the acceleration in total value, we are to combine both. We are to combine both. And in this subtopic, you will find that AT and AR are at the right angle with one another. At the right angle with one another. Now, as I did mention earlier, you will find that in this case, V is not constant. So you will find due to the changes in the direction, that is differences in value of V, and hence there will be what we call as radial acceleration. Why? Because there is a change in the velocity vector, quite similar to the previous idea that though the V is constant, listen carefully, the V is constant, yet it changes velocity direction, you have acceleration, yet you call it as centripetal acceleration. However, here we call it differently, where it's called as radial acceleration. And you would note that they have the same value. It's just that their direction is in the opposite direction. And that is the idea. So in this situation, you will find that the value given here, AR, AT, and the total acceleration here indicates the situation of the instantaneous at that moment, at that particular moment, because we find that the V is changing every second, every second. So coming back, right? So the whole thing here, the equation gives instantaneous, centripetal, acceleration, different. So the value of that instant. Okay. Right. So which equation that we are expected to use? So here goes. Remember the idea that I did mention earlier that A tangent, AR are at the right angle. So you will find that the total acceleration here is the combination, right? So of the hypotenuse AR and AT, and this is the expression that you are going to use. In that sense, okay, to make comparison with the previous, when it's uniform, in uniform motion, when V is constant, so we will find that AT, there is no value. AT is 0. What is AT medium? Now, if all in the linear motion object, all in the linear motion object, so AT would be 0. But here, when it's not constant V, so you will find there is a value of AT. Okay, let's have a look at example, and you will find that this example portray similar methods in calculation. Okay, however, it's just that we have an additional concept, we call it as A radial, and this A radial has the same magnitude as centripetal acceleration, just that their direction is different. Okay, example 4.7, over the rise, a car leaves a stop sign and exhibits a constant acceleration. Okay, a constant acceleration. Okay, this is photo. Don't know what's wrong. Alright, a constant acceleration value 0.300. This indicates that you have to consider in your work at least a minimum of 3 decimal places before you proceed for your final answer. The car passes over a rise. So this is the rise. And the top of the rise shaped like an arc of a radius 500 meter. At that very moment, when the car is at the top of the rise, the velocity vector is horizontal, indicates here, to the circumference and has a magnitude of 6 meter per second. Question, magnitude and direction of total acceleration only during this instant. Only during this instant. So you will find your final version of calculation. To calculate A total required you to substitute AC or AR plus AT, because according to the figure, we find that A tangent occurring horizontally as such, while AR radial occurring tangentially to the occurring towards the center. And due to that, the total acceleration is a product equivalent to the hypotenuse or trigonometry of the shape. Okay, and as you can see how we substitute, okay, so this is v squared over r, which is equivalent to centripetal acceleration, except that it has negative. And the moment you substitute, observe that you have to square the value. So the negative effect will disappear. And then just add on to a tangent given earlier, and you are going to get this answer. Now, how about this particular direction? So go back to the picture. So here you will find that AR over AT, giving you an answer negative 13.5. Negative 13.5. Right. Now, the answer is negative because according to our figure, if you are to sketch, the reading is below of the negative axis. Okay, below of the negative axis. Now, we can put down negative here because we have a proper figure. In the case that you don't have a proper figure, let's say that this question is repeated but yet without figure, then it's okay not to put negative 13. So you can simply put as positive 13.5 because you are not that sure of the direction in terms of how to read the angle, but you are aware of the angle itself. Alright, okay, that's the examples, and these are not within the syllabus. That's it, guys. Thank you very much.